Okay, so let's solve the problems of worksheet A. And let's begin with finding the directional derivative for the function f of xy equals ln of xy minus 5. We want that at the point 2, 3 in the direction of the vector square root of 2 over 2, square root of 2 over 2. This is what we want to compute. So we know that this directional derivative is the same as the dot product of the gradient at that point with the direction vector. That's what we want to compute. So the question is, what is the gradient? And we know by definition that the gradient is the vector whose whose components are the partial derivatives at the point under question. So let's find those partial derivatives. Chain rule, the usual chain rule, 1 over xy minus 5 times y, which means that f sub x 2, 3 will be equal to 3, and f sub y will be 1 over xy minus 5 times x, and f sub x, f sub y at 2, 3 is going to be 2, which means that the gradient is simply the vector 3, 2. And the directional derivative that we're looking for is the dot product of 3, 2 with square root of 2 over 2 comma square root of 2 over 2. And this will be 5 square root of 2 over 2. Okay, when we multiply 3 times square root of 2 over 2 and 2 times square root of 2 over 2, that's 5 square root of 2 over 2. And that's it. Let's go to the second problem. And the second problem says that we consider the function f of x, y, z equal to xy plus z over x plus 2y minus z. And we want the unit vector, so find the unit vector that points to the direction of fastest decrease for f. So pointing to fastest decrease for f of x, y, z at the point 1, negative 1, 2. Computing vectors like this lies in the heart of neural networks. But in any case, back to our more mundane goal of solving this problem. Sorry about this Zoom issue. Unfortunately, this is something that comes up every now and then. But in any case, the bottom line is that the direction of fastest increase is that of the gradient. The direction of fastest decrease is the opposite of the gradient. So here what we want to find, enough to find the opposite of the gradient, but at the given point. But don't forget that you need to normalize it. So you need to divide because we want the unit vector, right? And this is -2 actually. I should be careful with the numbers. Okay. This is the vector that we want to find. So let's begin by finding the gradient. So what is f sub x? Use your quotient rule. And that will give you the derivative of the numerator with respect to x will be y times the denominator minus the numerator. Oops. Times the derivative of the denominator, which is 1, divided by x plus 2y minus z all squared, which means that f sub x at 1, -1, -2 will be how much? So we have the number -1 here, multiplied by 1, and then we have minus xy, which is -1, plus z, which is -2. So -1 times -1 minus -2 will be -3 times 1 divided by 1 squared. So this is going to give you -1 plus 3 is 2. Okay. Okay, 2 more to go. Let's see. F sub y. Now find the derivative with respect to y. It's going to look like x times x plus 2y minus z minus xy plus z times 2. That's the derivative of the denominator with respect to y, divided by x plus 2y minus z all squared. So this will give you f sub y at 1, -1, -2. It's a very similar computation. So we will have 1 times 1 minus -3 times 1 over 1 squared. So that will be 1 plus 3, which is 4. And finally, let's find f sub z. Again, one more quotient rule. So the derivative now of the numerator is going to be 1 times x plus 2y minus z minus the numerator times the derivative of the denominator with respect to z, which is -1 over x plus 2y minus z all square. So f sub z of 1, -1, -2 is going to be 1 times 1 minus -3 times -1 divided by 1 squared. How much is this? So you have 3 negative signs here. That will give you minus, so that will be 1 minus 3. That's -2 on the top divided by 1. That's -1, which means that the gradient at the point 1, -1, -2 is going to be 2, 4, -2. And we need to normalize this vector pretty much. So there's this old trick. If you want to normalize any vector, it's the same thing as normalizing any scalar, any positive scalar multiple of the same vector, which means this is 2 times 1 to -1. It's the same thing as normalizing this, in other words. And the normalization of this vector is got 1 to -1. Its magnitude is square root of 6, and you want to take the opposite of this. Okay, and that's your final answer. So it's going to be -1 over square root of 6, and -2 over square root of 6, and 1 over square root of 6. That's the vector you're looking for. Again, and let me just say that if you want to normalize, so if you have a vector u which is different from 0, normalization of u is exactly the same as normalization of lambda u for some lambda greater than 0. Okay, if you think about it, normalizing a vector means take the unit vector that points exactly in the same direction, right? So if instead of the original vector you had, let's say, this one, they will both have the same normalization, which is this. It's a very simple principle that can make your life much easier. It wouldn't have been a big deal. I mean, you would have got a slightly more complicated fraction, but it would have been perfectly fine. Let's go to problem number 3 now, which says to find an equation for the tangent plane to the graph of, so tangent plane to graph of f of xy is equal to x squared minus xy at the point 2, 1, 2. Here, it would be a good idea to know what we're looking for. So I should say such an equation is given by z will be equal to f2, 1. The point that you have is 2, 1, right, for f, and the number 2 here that you have is simply f of 2, 1. That's how we form the graph, right? We juxtapose the inputs with the outputs, so it will be plus f sub x at 2, 1 times x minus 2 plus f sub y at 2, 1 times y minus 1. So basically, we know that f of 2, 1 is 2, and we need to find the other two numbers, right? So we need to find this number and this number. By the way, this is the graph of the linear approximation. So what you have on the right is the best linear approximation for f at the point 2, 1. Okay, this is quite simple. What is f sub x? F sub x will be just 2x minus y, which means that f sub x at 2, 1 is going to be 4 minus 1, also known as 3, and f sub y is going to be minus x, which means that f sub y at 2, 1 is going to be negative 2. So now we have all the numbers, and the equation for the tangent plane will be 2 plus 3 times x minus 2 plus negative 2 times y minus 1. And that's it. I mean, someone might ask here, do we need to simplify it? You can simplify it if you like. It's not really a big deal. Let's go to problem number 4 now, and which is to find and classify the critical points of the function f of xy is equal to x cubed plus 6xy minus 8y cubed. So this is, so find and classify the critical points. So let's take a look at the solution. What we need to do first is find the critical point. So let's find f sub x, which is going to be 3x squared plus 6y, and f sub y, which is going to be 6x minus 24y squared. We need to set them equal to 0. That's what it means to have a critical point in this simple setup, meaning it means to have both partial derivatives equal to 0, or equivalently the gradient being equal to 0. Okay, and here we have a very simple situation. You just need to solve for one of the two variables and plug into the other equation. I think it's a little simpler to solve for x. Solve the second equation with respect to x. You will get x is equal to 4y squared, right? Divide by 6 first, and then take this 4y squared and plug it into the first equation. So that will give you 3 times 4y squared plus 6y is equal to 0. 4 times 4 is 16, 3 times 16 is 48, 48y cubed, y to the fourth, sorry, plus 6y is equal to 0. Simplify this, 8y to the fourth plus y is equal to 0. And this will give you y times 8 y cubed plus 1 is equal to 0. So either y equals 0 or 8y cubed plus 1 is equal to 0, which means that y cubed is equal to negative 1 over 8. If you have a negative number, there is precisely one real number, which is its third power, which is its third root, which is precisely minus the cubed root of 1 over 8, which is minus negative 1, minus 1/2. Okay, so either y equals 0 or y equals 1/2. Now, if you have those, then you can easily find what x has to be from the second equation, meaning the second equation, remember, I told you that x is equal to 4y squared. So if you plug in y equals 0, so if y equals 0, that will tell you that x is 0, giving the point 0, 0. So that's one critical point. And if y is equal to negative 1/2, then that will tell you that x is equal to 4 times negative 1/2 squared, meaning 4 times 1/4, which is 1. So that will give you the point 1 comma negative 1/2. Okay, so we have our two critical points, and now we should try to apply the second derivative test. In order to apply the second derivative test, we need to find the second derivative. So what is f sub xx? Well, take f sub x and differentiate it with respect to x once more. That will give you 6x. And take f sub x and differentiate it with respect to y. That will give you the constant function 6. And take f sub y and differentiate it with respect to y. That will give you negative 48y. So let's take point by point. So for 0, 0, what is d? Let's write it once so that we can see it. So it's f sub xx at 0, 0, f sub xy at 0, 0, f sub xy at 0, 0, and f sub xy at, I'm sorry, fyy at 0, 0. Let's put these numbers together. So we will get 0 here and 0 there. And then we will have a 6 here, a 6 there. When you find that determinant, you find negative 36. That's less than 0. This is what we call a saddle point. So we have no extremum, no local extremum here. I also like to call it Pringle point. If you think about it, it's pretty much the same shape that you have in a Pringle, meaning you have two directions, one that suggests that you have a local minimum, another one that suggests that you have a local maximum, and eventually, because of that reason, it's neither. So let's move to the second critical point. We have our derivatives. We need to put again this derivative, this determinant together, the determinant of the second derivatives. Hence, we call it the second derivative test. An analog of the second derivative test that we have in one variable, however, one has to know that the function, the reason that we take this determinant is different. We simply try to find if we have the same behavior in all directions. That's what this determinant gives us. And if we do have it, then we just sample one direction to see what eventually we have. When do we have the same behavior along all directions? If this determinant is positive. So let's see what this determinant is going to be. So the partial derivative with respect to x is 6x, so that will give you a 6 here. The constants that you have are being preserved, and fyy is negative 48y, plug in negative 1/2, and that will give you 24, right? So you get 6 times 24. How much is 6 times 24? 144, right? But it doesn't really matter. It's 144 times minus 136 or minus 36, which is certainly greater than 0. The fact that it's greater than 0 tells you that you have a local extremum, and the question is what local extremum you have. This is where you sample one of the second order partial derivatives with respect to the same variable. So for example, fxx, it's 6. So you can write that exactly because this is positive, that means a local minimum. Sometimes people think that this is a little counterintuitive. So greater than 0 local minimum, less than 0 local maximum, but it's not. Because remember that second derivative being greater than 0 means that you have the shape of a, that's concave up, shape of a smile, right? A smile means exactly local minimum. If the second derivative is negative, then you have the shape of a frown, and that is the shape of a local maximum. Okay, let's go to problem number 5. So we want to use the method of Lagrange multipliers in order to find the minimum and the maximum of the function f of xy is equal to x squared minus y squared on the ellipse, or if you like, under the constraint x squared plus 2y squared is equal to 4. Okay, so how do we deal with such a problem? The very first step that you need to do is define a function that gives you the constraint. So define g of xy, bring everything to the left-hand side. So I think the easiest thing to do is bring everything to the left-hand side and set that as g. Okay, and there you go. And finding the critical points that are subject to that constraint is the same as solving the system of the gradient of f being parallel to the gradient of g and g being equal to 0, right? So eventually this breaks down to 3 equations because the gradient of f is 2x comma negative 2y. The gradient of g is 2x 4y. And g being equal to 0 simply means x squared plus 2y squared is equal to 4. Okay, so what is the system that you get? 2x is equal to 2 lambda x, and negative 2y is equal to 4 lambda y, and x squared plus 2y squared is equal to 4. How do we solve such a system? There are different ways to solve such a system, but usually you want to come up with equations that are simpler, that have fewer unknowns. Here in this case, The easiest thing you can do is actually start with the first equation, divide by 2. So that will give you x is equal to lambda x, and then bring everything to the left-hand side and factorize. So that will give you x times 1 minus lambda is equal to 0, which means two things. X is 0 or lambda is 1, right? Because one of these two factors has to be equal to 0. So if x is 0, then you go directly to your constraint and you find 2y squared is equal to 4. So you plug it in here. And this means that y squared is 2, which means that y is plus or minus square root of 2. So this immediately gives two critical points, 0 square root of 2, 0 negative square root of 2. Okay, so let's put this in a frame so that we don't forget them. And if lambda is equal to 1, now this is kind of interesting. Now you go to the second equation, and this will give you minus 2y is equal to 4y, which means that 6y is equal to 0, which means that y is equal to 0, and you have something quite similar to what we just did. You go back into your constraint that gives you x squared is equal to 4, which means that x is equal plus or minus 2, and that means that you obtain the points 2, 0, and negative 2, 0. So now you have a total of 4 points, and what I like to do in such a case is put them in a nice table and plug them into the objective function. Objective function is the function that we're trying to minimize or maximize. So what do we get? So 0 comma square root of 2, 0 comma minus square root of 2, 2 comma 0, and 2 comma 0. And the function was x squared minus y squared, right? Okay, so we will get minus 2 here, another minus 2 here. We'll get a 4 here and a 4 here, which means that this is a maximum, not a local maximum, an absolute maximum over that ellipse, and this is a minimum. And this is the second point where we have a minimum, and that solves our problem. Let's go now to problem number 6. That should be a quick, fun problem. We want to compute a double integral over a rectangle. This is a rectangle that has sides 0, 1, and 0, 1. So we have x cubed minus xy dA. So write this as an iterated integral. This is a rectangle, you can start with any of the two, and since your integrand is a polynomial, you will not have a problem integrating. So you don't even need to worry about which one to. And that's it. That's your iterated integral, which means that we do the inner integral first. And this means that we integrate with respect to x. So that will give us x to the 4 over 4 minus x squared over 2 times y. So we treat y as a constant, and we want to go from 0 to 1. And this is going to be the integral of what? Plug in x equals 0 and x equals 1. So sometimes people like to write x equals 0 here, x equals 1. I don't always do it that way, but just for the sake of clarity. And this will give you 1/4 minus 1/2 y. And now you can clearly hand this to any friend of yours that has been through Calc 2 or Calc 1 for that matter. I mean, this is a linear function. You don't even need calculus in order to find that area. But anyhow, we're still using the fundamental theorem of calculus. You have 1/4 y minus 1 half squared y squared, right? That's the antiderivative, and you want to go from 0 to 1, and this will give you 0, right? Because this is 1/4, so it's 1/4 minus 1/4, so it's like 1/4 minus 1/4 minus 0 oops, minus 0, which is 0, is the final answer for this integral. And then let's go to number 7, where we have this very interesting situation. We give this in steps, and pretty much we want to compute this iterated integral. You have to remember that structurally speaking, an iterated integral is a little different than a double integral. An iterated integral is a concept that can be explained to anybody who has taken a one variable course. So it's not necessarily something that for which you need to talk a lot about double integrals. But here you have a conundrum. If you try to really compute this as an iterated integral, you're stuck with the antiderivative of e to the x cubed. That antiderivative is a perfectly existent antiderivative. It's just that we don't have a name for it. So that's where you get stuck. So now this is where the theory of double integrals comes in, and we ask ourselves, if this is an iterated integral, it most probably came from a double integral. So somebody chose to integrate first with respect to x, then with respect to y, and we cut this. Well, but why don't we try to go the other way around and see if it works better? To do that, the first thing that you need to do is sketch the region of integration. So you have to remember that when you have this iterated integral, you go from, and you're integrating in the x direction, we go from a left boundary to a right boundary. So the left boundary here is x equals square root of y. So the left boundary is x equals square root of y, and the right boundary is x equals 1. X equals square root of y, if that confuses you, just solve for y. It's x squared is equal to y, which is your usual parabola. So that's your left boundary, and the right boundary is a vertical line. And you can check that since the lower endpoint is 0 and the upper is 1, meaning, oops, again, this thing. Let's go back. Zoom is misbehaving a little. So since, and now it was my mistake. Let's draw this again. So I was saying that since this is really the point 1, 1, that tells you that your region of integration is this. And now you get a fresh start. You say, well, what if I try to go first with respect to y and then with respect to x? Well, if you try to do that, then that means that you will have an upper boundary and a lower boundary to deal with first. So your upper boundary is x squared, your lower boundary is 0. So you do vertical integration, and the range of all these vertical integrations, in some sense, the horizontal range of all these vertical integrations is from 0 to 1. And that's your double integral. And you might say, well, does that make a big difference? Oh, yes. Because now you're integrating with respect to y. And this is a constant, which means that the antiderivative is simply going to be y times e to the x cubed. And you want to go from y equals 0 to y is equal to x squared. And that is going to give you the integral from 0 to 1 of x squared e to the x cubed dx. And now there's a substitution that's so different than what we had before. So we have u is equal to x cubed, and du is equal to 3x squared dx, and x squared dx is the same thing as 1/3 du, and this is going to be 1/3 integral of e to the u du. Now, Sometimes people forget that when you have a substitution, you need to apply the substitution to the endpoints. Here, if you apply it, you get exactly the same things. Why? Because 0 cubed is 0 and 1 cubed is 1. So let me write it this way so that at least you remember that there is that you have to make this change. And this will give you 1/3. The antiderivative of e to the u, of course, is e to the u from 0 to 1. So that will be 1/3 e to the 0, also known as e, minus, I'm sorry, e to the first, also known as e, minus e to the 0, also known as 1. And that's our final answer. Okay. And our last problem, it says to compute the double integral over d of x squared plus y squared dA. Where d is the circle of radius three centered at the origin. The disk of radius 3 centered at the origin. Okay, so here we will just go through polar coordinates, and we will take into consideration that the domain D in polar coordinates is described how it's all the r and thetas, such that r is between 0 and 3, and theta is between 0 and 2 pi. Sometimes people might complain here and say, well, we should put a strict inequality for 2 pi. But the truth is that it doesn't matter because it corresponds to a subset of the region of integration that contributes no volume to the to the underlying integral. So we will have the integral from 0 to 3 dr. We will have the integral from 0 to 2 pi d theta. And the integrand is what? It's x squared plus y squared in polar coordinates. We know that x squared plus y squared is exactly r squared. That's the Pythagorean theorem, by the way. And of course, don't forget your Jacobian. And here, this integral is very, very simple. So you have r to the 4th over 4 from 0 to 3. And this is going to be 81 over 4. And you want to integrate this constant function 81 over 4 on an interval of length 2 pi. So that will give you the constant times 2 pi. You can also do a simplification, and that's the integral that we get. Okay, so that gives you the volume between the graph of the function x squared plus y squared and the disk of radius 3 centered at the origin. And that completes our set of solutions for the first set of problems. Thanks for watching.